Okay, well, that's the first thing that will be heard in a recording. Another Montefort classic. Um, I come across something in Facebook, but I think it was from, I forget what class it was. It might have been maybe 772 or something. Yeah, about orthogonal polynomials, and I said like not everything is zero, and yeah.
Yeah.
I don't know.
I don't remember that, but
I'll find it.
Okay.
Yeah. So, but yeah, it was a funny moment that you took part in or instigated. So yeah. Well, nothing will ever top the whole beans thing, but beans. Yeah.
Yeah. Haley told my husband about that, and he says it all the time. Y'all want some beans? Walk around the house all the time.
Yeah. Okay. So, all right. So as I said, for those of you who are watching this video, then I'm going to everything from the last notes I'm going to implement in MATLAB, and it won't be terribly difficult to do. And I'll be referring frequently to these notes for the details. So the first thing is if we have a function that we assume is defined on 0, 1, just evaluating it at 2 to the j equally spaced points, and those will become the coefficients in our representation of f in terms of the Haar scaling functions at that scale. So, so the first function I'm going to implement is, and I'm going to use a prefix Haar, because some of my functions have a very simple name like L, H, or L tilde, H tilde, so I'll use a prefix to distinguish. Why is my screen flashing? That's kind of weird and troubling. Okay, so maybe it's a projector that's doing that.
That's possible.
Yeah. Okay, we'll go with that.
Now, it could also be, this is the justification to use your mighty position as graduate coordinator to tell the university that they need to start providing
well, I
you don't really know the story about the computer he has now, then.
I'm joking around.
A recently new one, right? Because you had another laptop for that one.
Well, this I've had for a year and a half.
Yeah, that's recently new.
Well, okay.
I've had my computer since 2012.
Oh,
my
okay.
gosh, what a brand new computer. I mean,
swear.
you should have a computer at least dating back to 2005.
Yeah.
Oh, yeah.
Yeah.
Well, yeah, that's
So
true.
yeah, so this is because I had a disk crash in the middle of the day, shortly before class. So I raced to best.
And you lost that homework.
Yeah.
That's awesome.
Yeah.
Lucky students.
Yeah. So I had to race to Best Buy to get this one. Yep. So yeah, I was amazed it all worked out as well as it did. But yeah, I'm running out of disk space in this one. So, and that's what I get for not really paying attention. It says, "Oh, how many gigs of flash storage?" And I thought that meant in addition to some hard drive, not instead of. So,
Yeah.
okay, so my function, Haar sample. So I'm going to take a as input some function f, and we'll just assume it's some MATLAB function handle. So we can just plug in any x into it, and then I'm going to select the the resolution is indicated by value capital J. So 2 to capital J points in total is what we'll have. So that'll be the second input argument. The output. What?
The letters bigger.
Oh, right. That's right. I usually do that for a projector. Okay. Well, yeah, because each of these functions is so short. I definitely have plenty of screen room to use. Okay, let's try this. Okay. All right. So the output will be f capital J, and that's just going to be a. Okay, so function handle, and it should be vectorized. In other words, because I'm lazy, I like to be able to just write one statement that plugs a vector into a function instead of having to do like a loop, explicit for loop. So it should be a vectorized function handle, like standard MATLAB functions are. Okay.
There really is no
Yeah. And then the output will be fj, and that'll just be the coefficients. A, kj. So in other words, in this formula here, that these coefficients.
Does that come out as a vector?
Yes. And just for some, I like to work with column vectors because it's easier to see them on a screen. Read them on a screen. Okay, so I can do this in just one line. Kind of like name that tune. I could name that tune in 3 notes. You know? Yeah. So several of these functions really will be literally one line. So all I have to do is first I need to so I can build it from the inside out. I need these points. So k over 2 to the j, where k assumes these values. So I'll just take this. Well, okay. On my cheat sheet, it's one line, but for clarity, maybe it's allowed to be a little bigger. So first, I also want to correspond to the notes. So k would be 0 up to 2 to the capital J minus 1, just like this k here. And I'm going to make it a column vector, since my output will be a column vector. And then I'll plug that k over 2 to the capital J into f. So, k over 2 to the capital J. Now this will give me a column vector as output, and well, that's it actually. So, so these are the coefficients. Actually, I'm going to well, for clarity, I'm going to call it AKJ. Okay. Of course, well, I'm allowed to use underscores in variable names. I cannot use the caret for superscripts. But, okay, so there you have it. So now we have our coefficients. So now we have the function f in this form. So now I can go ahead and work with it. So step 1 is done. Okay. Oh, before I go any further, I meant to do this at the very beginning, just as an announcement. So I will not be covering any more new material. So the plan is, well, whatever time I have left today after this MATLAB stuff, well, will be homework questions. Monday, I'll be here for homework questions. If nobody has homework questions, there's no class.
I'm planning on sending you frantic homework questions at 2 and 3 in the morning.
Okay. Well, then I'll answer them around 6 or 7.
I emailed him at 7 o'clock on Saturday morning. That's when I get to do my homework. So.
Yep. Oh, yeah. Well.
Yeah, it's usually that Friday morning.
Yeah, we all are weird. Yep. Yeah, I'm awake. So, and then that's the Monday before Thanksgiving. Monday after Thanksgiving will be a review. The Wednesday after Thanksgiving, which is the last class period we have, is when the final exam begins. So I guess I need to write that. Okay. Now, okay. So now we move to the next stage, decomposition. So breaking down f from this form into this form, and computing all these terms involves these operators, the downsampling operator, then the L and H. So what will happen is I have a set of A's at the finest scale, which leads to A's and B's at the next coarser scale. That gives me these terms. So I need functions for these operators, D, L, and H. So I'm going to do those first. And then once I have that, then I'll be able to implement the rest of decomposition with not much trouble. Okay, so more one-line functions coming up. Okay, so done with you. So first, downsampling. Okay. Okay, so downsampling will. Okay, first I'll go back to the notes for here's downsampling. All it does is it takes in some sequence X, returns sequence of only the even numbered terms. So I'm going to assume that X is our input. So we have the sequence that consists of x0, x1, up to xn minus 1, where n is whatever length of the sequence that we have. And then I'll call the output y. So that is a sequence where we have x0, and we just take every other element. That's what downsampling does. It takes only the even numbered elements. I'm going to assume that n is even. Also, okay. Well, so for instance, if I have x0, all right. Let's suppose that n is equal to 16. So I have x0 to x15. So then I want my output to be x0 to x7. Okay. So very easy to do in MATLAB, especially. All I have to do is I start from the beginning, because the first element will be taken, and I take every 2 all the way to the end. That's it. So not very interesting. Okay, so downsampling zones. So return to sequence of half the size. Okay, now, actually, I want to make. Okay, I assume it's recording. Better be. I know I hit the thing. So, all right. Now we also have these operators h of x and l of x, and have these nice formulas here for whatever input sequence x that we have as defined in a similar way. Now, if x has n elements, the output of both of these will also have n elements. But what I'm going to do is, these are defined for infinite sequences, but I'm going to assume that these sequences are defined on the domain, like k goes from 0 to like n minus 1. So then when I take the last element, that this will be 0. So outside of that interval, I'll assume that the elements of x are all 0. Okay, so first this operator h, and then once I do that, L will be particularly easy. So I just change a minus to a plus. Big changes. So my operator h. So input sequence x, output sequence called y. So when I take the kth element, first I just have 1/2 times x itself, and then I have x shifted. So what I need is starting from element 2, going all the way to the end. Because here, the first element would be x1, here would be x2. Now, you have to put your MATLAB caps back on. This is MATLAB indexing, not Python. So, as some have some difficulty with. Okay, but what about the last element? So this would be x, the last element, and in here, we won't have anything. It'll be 0. So I'm going to take this column vector and slap a 0 on the end. And that takes care of that. So that's the end of that function. And in fact, what I'm going to do is I'll make a copy of this. Well, actually, I don't even need to do that. I'll do a save as and get Haar L. And all I got to do is change a minus to a plus, because that's all we have here if it's any different. So now we have the building blocks for decomposition. So what I need to do for decomposition, I'm going to implement it using 2 functions to make it easier to see. Because what happens is, first we break f down into f at 1 level lower, and then a w. So f gets broken down into 2 pieces. Then we take what remains of f, break it down into 2 pieces, and we keep going until we have all the pieces. So these equations, right? Okay, everything I've highlighted here describes one stage of its decomposition, where I take f at scale j and break it down into f at scale j minus 1. So I have my coefficients from scale j, feed it into these operators, and get my coefficients at scale j minus 1. That gives me these pieces. And then what I get from this, its coefficients of these a's here, get fed back into this to get coefficients at scale j minus 2. And I keep going until I get my coefficients at level 0. And then I'm done. So I'm going to implement a helper function that does this part, basically. And I'm going to call that decompose pass. So one pass of decomposition. And all this function has to do is implement these two lines right here. So I have coefficients A coming in, and coefficients A and B coming out. So scale J is coming in, scale J minus 1 coming out. And all I have to do is code up these two lines. But I already have the operators, so there's actually very little to do. I just call those functions. So, and I'm actually going to implement, because I'm going to overwrite the old A with the new A. So I'm going to do this line first, because I could do these in either order. So I'll set B equal to downsample of H of A. And then A is downsample of L of A. And that's it. So, so that performs one stage of a decomposition. So now, to do the actual decomposition, I just need to carry this out in a loop. Now, storage of my output is going to be interesting because I have, okay, so fj is what's coming in. Really, its coefficients are coming in. My output, I'm going to have f0, which is actually just going to be one number. It's going to be one coefficient. And then I'm going to have, okay, so capital W will hold, it's going to hold the coefficients for all the W's. So these are the coefficients coming in. Going out, we have f0, which is really just a 0, 0. So one and only coefficient we have at that level. And then capital W is going to be a MATLAB cell array consisting of W0, W1, W, I'll put subscripts in here. But each one of these really are going to be column vectors of coefficients. So I'm going to have B0, B0, B1, Bj minus 1 as column vectors. But the reason I have to use a cell array is all the column vectors will have different lengths. So I have one element, 2, 4, and so on, all the way up to 2 to the capital J minus 1. That's a minus in this one. So that's why I have to use that unusual method of storage. Okay, there's a little bit more involved here, but still not much. So first, I need the number of levels, capital J. And all that is that's a log to base 2 of how many elements we have coming in. So we don't need to pass it as a parameter. So that tells us how many passes we're going to have to make. I'm going to pre-allocate W to be a MATLAB cell array, has J elements to hold all these components here. And then, so it's a one-dimensional cell array. And now I do my loop. So all I do here is I call my function to perform one pass of decomposition. Fj gets passed in. The updated Fj and the coefficients of w, each new w, are the output. And now I just handle storage. So in my cell array, I store it here. And the reason why I have this funky indexing here is I want W0 to go first in a cell array, but actually compute it last. This comes first. So when little j is equal to 1, the last element gets filled in first. So because I'm filling in backwards, I have to do this for the indexing. So Fj, in terms of size, keeps getting cut in half till so they get these a coefficients at coarser and coarser scales until finally we have one number left, and that gets stored in F0. And that's it. That's the decomposition. So any questions about how this
Where
proceeded?
did the D come from with the other operators? DL, DH?
Oh, D and L are separate operators.
Yeah.
Oh,
What's D?
downsample.
What,
Um,
that was the first part? I saw the code for it, and I saw you called downsample. I just didn't know exactly what code was in it.
that implemented this
Okay.
to take every other entry. Yeah.
Gotcha.
Okay. All right. Any other questions about decomposition? So now I'll demonstrate the use of all of these after they're all implemented, and we'll see how we have sort of all of these as a package that consists of all of these W's and then the one F. Now, processing I'll hold off on. I kind of do that like at the prompt. I'm going to handle reconstruction. Reconstruction works quite similarly to decomposition, it's just that everything is backwards. We have these operators, U for upsampling, and then L tilde and H tilde. So I can implement these building block operators that are described here for reconstruction. So starting with upsampling, upsampling, you take a sequence X as input, and basically you're splicing it with zeros. So you have the first entry, really the zeroth entry, is the zeroth entry of X, and then followed by a 0, then X1, then 0, then X2, and so on. And MATLAB, again, makes it very easy to do this. Okay. So Y will be the output, X will be the input. So X is a sequence consisting of X0, X1, up to that, where n is the length. Y is also a sequence that has X0, 0, X1, 0. So has two n elements altogether.
That's not the same X from downsampling?
Well, okay, so really what's happening is outputs of previous downsamplings, if untouched by processing, will be fed in as inputs to upsampling. So it's a big old undo.
That's what I was asking, because would the elements in the upsampling not be even, or we just re-index them?
Each output of downsampling still is even because we start with a power of 2 and we keep cutting in half until we get all the way down to one entry.
For the D?
The output of D.
Okay.
And yes, so downsampling cuts in half and then this doubles. Oh, this should be upsample. Okay. So what I'm going to do is, since I don't like to use explicit for loops, I'm going to do the following. I'm going to take X, Now x is a column vector, keep in mind. And I'm going to...
No, I don't.
What?
How is x in my? How is it linked in -1? If we cut it in half.
Wait. Oh, this is how... Okay, this is an indexing that'll be used like mathematically, like in the notes.
That's not actually what's in there.
Like in MATLAB, it would be referred to as x1, x2, up to x capital N.
Not that, but I'm talking about, wasn't x cut in half by downsampling?
Oh, yes, it was.
So would it not be linked in?
Well, okay. N here refers to whatever length this happens to be. Because it gets called many times, always at different lengths. Okay. All right. So we have the column vector, and then I'm going to slap a column vector of zeros next to it, same size. Now, the next thing I'm going to do is okay. All right, and then I'm going to transpose it. So now I have a matrix of 2 rows. X is in the top row, all zeros in the bottom row. Then all I have to do is reshape it into a column vector. The reason why is when you have a matrix of whatever size and you reshape it into a vector, it's going to go column by column. So after I transpose, first column is x0 with a 0 below it. Next column, x1 with a 0 below it. And by cycling through column by column, I get the form that I want, where elements of x and zeros alternate with one another. So taking advantage of how matrices are stored in MATLAB, it's called column major order, column by column, as opposed to like C++, it uses row by row, which is also the default in Python. Okay, so any questions about why that worked?
So, if it was by rows, what would you do?
Okay.
Would you do a modular, or would you do?
If I still wanted a column vector to be the result, probably the best thing to do is not transpose.
I was about to say that.
That would be enough. Yeah. Because I'm still telling it by this, the output must be a column vector. Yeah. So very easy to do. Okay. Oh, good question. All right. So that's upsampling. Now I need these operators h tilde and l tilde. Similar to h and l, there's no 1/2 here. Instead of working with xk plus 1, it's xk minus 1. And they only differ from each other by the sign in between. So I'm going to call this capital HT, T for tilde. So input sequence X, output sequence Y. So all I have to do is, so I have to take X as a start, and I subtract off X shifted, but shifted in the opposite direction from before. So now the first element of a shifted sequence is going to be 0. And then I have X from 1 to the n minus 1. Okay. Because what happens here is first element would be x0 minus x sub minus 1, which is 0. So that's why we won't have anything contributed here. And that's it for that function. And then I could do a save as to get L tilde. And all I got to do is change a minus to a plus. And now I have my all my operators, my building block operators for reconstruction. So now I just, for one pass through reconstruction, I just do this. So that'll be, so just like with decomposition, I'm going to make a function for one pass of reconstruction that will have very little to do. So in decomposition, we took A as input and we returned A and B as output. Here's the opposite. A and B are input and only A is output. So I'm just going to implement this line here. So L tilde upsample of A plus H tilde upsample of B. So, so L tilde upsample of A, H tilde upsample of B. All right, so that's one pass of reconstruction. And now for the full reconstruction. Okay, so this is the output, back to a finest scale. And the output of decomposition is what gets passed in. So as far as the number of scales, that would just be the number of elements in capital W. So I'll just take its length. And then my initial reconstruction will just be starting at F0. And now what I need to do is, for reconstruction, okay. Once I get my coefficients, my A's, that's really all I need. So I just keep performing this. So I have my loop where I take one pass of reconstruction with Fj, and each element in turn of W gives me my B's. And that's it. So I've actually implemented all the functions. So I could do sampling, decomposition, and reconstruction. So what happens here for reconstruction? Okay, yeah. So really what's happening is the coefficients of F0, W0 come in first. I use those first and carry these out to get my coefficients at level 1. Then I throw in the coefficients from W1 with these coefficients at level 1 to get the coefficients at level 2. And I keep going through all these terms until I've exhausted all of them. So each time I go through a loop, my number of coefficients in Fj doubles. Okay. Now, I'm going to create a function so we can actually try these out. Next example I tried when I tested this wasn't very interesting, so I'm going to try to make something more interesting and see how it goes. So I'll make a function of x, and we'll do something simple like the actual signal will be sine x, and then I'm going to add some noise to it, but something pretty small, like, okay, maybe not that small. Let's say, okay, so that's my function of x.
So what on the inside with x is how many times it occurs?
I mean like this?
Sine and cosine.
Oh yeah, it indicates frequency.
Frequency, that's how many times it happens in between periods.
Right.
What does the 0.1 tell us?
Oh, that's amplitude.
Amplitude.
Yeah. Yeah. Okay. But yeah, I guess probably back in like. Okay.
I never took trig in college.
Oh.
Last time I took trig was my 10th grade year.
Oh, that's when I took it too. Yeah.
2010.
Wow.
I couldn't remember if it was in fall or spring, okay?
Yeah.
No. Books were invented for a reason.
They were.
And on top of it, I think that everything that's covered there has probably also been applied in other classes.
Let me tell you, I have a trig book. Okay, so I've taken the first step in reading it. Just haven't read it yet.
Look, the first step, but is it the right trig book?
I don't know about that.
the white one always starts with Gelfand's name on the cover.
What?
Okay.
Well, Gelfand, Israel Gelfand,
Okay.
who's Soviet mathematician.
Oh, okay.
One of these geniuses that actually decided to write a series of introductory books. So,
Oh, okay.
you know,
So this is a good introductory level
well, yeah, they're introductory level. He says high school
for
students.
Americans, not Soviets.
Well, it's translated from the Russian into English. So,
Yeah.
but at our level, we like to brag about who we're reading.
Oh.
And a lot of those introductory books, you cover them with shame, hold them behind, behind cheap magazines just so that no one will know that you're reading them. No, with Gelfand's name on it, you can hold it up proudly and say, "Yes, I'm reading a real mathematician."
Okay. Well, that's good to know.
I'll look into that.
and I was able to find all of them online for free. Well, most of those books.
I thought it should start from Pythagoras theorem.
What'd you say?
I thought it should start from Pythagoras theorem. The trigonometry.
Oh yeah. Well, we could just tell them, here's a book by Archimedes, and maybe Apollonius is kind of useful, and Ptolemy talks about chords, but I think that might kill the poor kids. So.
Well, it doesn't take much. Okay, so what I've done here is now I have my function. I've chosen I work with 256 or 2 to the 8th points. So I'm going to call sample variable. All it does is evaluate this function at 256 equally spaced. Oh, whoops! I forgot to use my Haar prefix. Okay, and let's go ahead and plot this because these are actual values. It's actually a little disappointing. I want more oscillation than that.
It's kind of doing what you expect.
Well, because by going from 0 to 1. Okay. Well, okay. Let's get a little more ambitious here. Better. Okay. All right. So, if I do this as a smooth curve, okay. Yeah, it's just all right. I can add an extra layer of noise. Okay. So 250x. That's more like it.
Yeah,
Okay. All right. So now what I'll do is, okay, I'm going to do decomposition. So I'll have F0 and W is hard decompose of F8. Okay. So if I look at F0, it's just one number. That's a coefficient that would roughly be the average value. And then W is a cell array consisting of 8 cells. Each one is a column vector that has double the number of entries as for one before. So a grand total of 256 coefficients in here. So if I were to plot these, let's see. If I look at the last one, so this is the detail that comes in at the finest scale, and then at coarser and coarser scales as I go. Okay. Just because we have fewer and fewer entries. Okay. So what I'm going to do is I want to perform some. I discussed two signal processing tasks. One is denoising, where we just cut out the highest frequency parts, and then there's compression, where we get rid of the smallest coefficients. Now, if I look at these coefficients, like if I look at in here, there's coefficients of varying magnitude. Some of these perhaps could be dropped. If I here, okay, these are all of a reasonable magnitude. They're not. They don't seem to be all that negligible. Okay, so because that kind of signal. So what I'm going to do is I'm going to. I have 8 levels here. So what I'll do is, as a quick denoising. Okay, I have W0 up to W7, so 8 altogether. So I'm going to cut out the last 2. So this would be a way to take the first 6 elements out of the 8, extract them, dump them in another cell array, and for some reason I played around with this last night. Cell arrays in MATLAB are kind of infuriating, to be honest. I needed to transpose it to have the exact same structure as before. So now what will happen is I can carry out a reconstruct with F0 and this W as parameters. And now, okay, so what I'm going to do is, in figure 1, I'm going to plot the original. Okay. And then in a separate figure, so we see how the general character of a signal has been preserved, but the highest frequency oscillations have been removed. Okay. So depending on how much you cut out, that's what kind of indicates the resolution of a signal that would be preserved. So now one could argue that maybe these features here should not be considered noise. Maybe I should. Now, if I had chosen a smaller coefficient, I just put like 0.05. If I put like 0.01, but something that almost certainly could be dismissed as noise. But at least you see how the process works in terms of preserving features up to only up to a certain resolution. Actually, I'm going to try. Okay, I'll try making another signal. So for this, I need another function handle, but I'm going to make an M file for it. It'll be easier that way. Okay, so I need to make this vectorized. So I'm going to take the length of x. Oh, actually, I still need the length. So first I'm going to start with a 0 vector. So in other words, the signal will be 0 over much of a domain. Somewhere in the middle, I'm going to add some stuff. So, let's see. And I'm going to assume for convenience that n is a power of 2, just so I can freely divide it by powers of 2. It's like, so I'm going to set those elements in the middle to be 1. Actually, no. Only up to n over 2. Then I'll put 0.5 here. And then I'm going to throw in some noise. Whoops, that should be lowercase y. 0.1 times
Why is there a 1 in there? In the middle?
Oh, that should not be there. Oh, plus 1.
Okay.
Yeah, so I go up to n over 2, the next element would be 0.5. Okay, so I have something very high frequency there. All right, let's see how that looks. So now I could do F8 equals Haar sample my signal with resolution 8. Okay. Let's see what that looks like. All right, that's pretty good. Although I want to make the noise a little more haphazard. So I'll throw another term here. I can make up a random number. Okay, throw a frequency.
Random number generator. Really random.
Okay, I like that. That's a little more chaotic there. Okay, so now what I'll do is do my decomposition. Okay, so if I look at the coefficients now, so the last element is the finest level detail. Okay, so coefficients varying size there. Same with W7. I'd like to find out what resolution would be necessary. Because notice the coefficients are getting even smaller. And here, coefficients are quite small except for that one. Oh, here they're all 0 except for 1. So if I was compressing, I'd toss these out. Or at least 0 them. Okay, so what I'm going to do is, again, with denoising, I'm going to cut out the lowest 2, and then I'll reconstruct. Okay. Dang it. Okay. And then I'll plot that. All right, so that was enough to mostly remove the noise. There's still a little bit of oscillation left, but yeah, this doesn't go straight up, but it did a decent job. What would happen if I cut out one more layer? Okay, so if I look at this figure again, yeah, it's getting a little haphazard there, but nothing perfect with wavelets. So, but yeah, but certainly if this was audio, this ought to be a much sharper signal than the one we had. So, okay, so, but yeah, but when I was looking at the coefficients of this one, it would really, if we want to remove a noise, we could also take this and compress it pretty well. Because if I look at W1, okay, that's important. W2, yeah. So here I'd only need one term from level 3. Here I might decide to only keep this one and toss the rest because they're small. And same thing here. I could see keeping this one. Let's see how that works. If I were to, okay. I'm going to make a loop here. Well, okay. I'm going to copy that. And then I'm going to let's see. I'm going to pull that column vector out. Go through that column vector. And if it's of a certain size, less than let's say 0.1. All right. So now I've gone through X and cleaned it out. Then put it back in there. Okay, so now if I look at, see, it's almost all 0. Oh, that one's entirely 0. I'm not sure how I feel about that. Did I screw up?
No. Let's be confident in our zeros.
Okay, because when I was looking at it before, like, okay, if I compare, like that one should have stuck around, like 0.01. Oh, 0.1. I should have said 0.01. So I did screw up. Okay. Dang, now I gotta do this again. Okay. Okay. All right, yeah. Okay, so that one sticks around. Why is it not cooperating? Okay, if it's less than 0.01. What am I missing here? Like that one would stick around, but that should not. Okay.
Oh, you got a J in the first one instead of
Oh, that's why. All right. One more time with feeling. Okay. All right.
And that is why you create the zip file, students.
Okay, I had that coming. Yeah, I don't usually mess up this many times and call it the prompt. Okay. All right. Third time's a dang charm. Okay. All right. Now, reconstruct with WD. Okay. So, all right. So this figure. Interesting. Wait. How could they be the same? That's freaky. Oh, that's right. I also want to cut these two out. I didn't touch these from a denoising standpoint. Okay. Okay, now yes, finally. This is what I was looking for. And somewhat better behaved than the other non-denoised signal. So okay, well, that was fun. But we can see that from 256 original coefficients, if we look at what's non-zero, so we need to have f0, so that's 1, 2, 3, 4, 5, 6, 7, 8. 8 total terms are enough to represent this signal exactly, and therefore capture this signal exactly except for the noise. So that's just the beauty of wavelet processing. Okay, questions? I'll post this code later along with this script with my embarrassments removed. Okay. All right. Okay, we have some time. Any homework questions? Okay,
Number 14, part D.
part D. Okay.
I think I get the rest of them. It's just when it says generalize this result, I'm always a little disillusioned.
Okay.
I just don't know exactly what they're doing. That's only how much you generalize like the eigenvectors
Yeah.
and the diagonal FFT. It says generalize this result. Yeah.
Yeah. So. Yeah. Okay. And really, well, I guess it's, the same hint I gave you earlier. But this is, this is a circulant matrix, and you can actually look up in Wikipedia a formula for the eigenvalues and eigenvectors of a circulant matrix. So, and with these particular coefficients filled in, if you didn't have that, so then what you'd be doing is carrying out that. So really, if you think of a DFT as from a matrix multiplication point of view, then the columns of a DFT are eigenvectors of a circulant matrix. So that would mean that carrying out the DFT on this would equal. So basically, what you're doing is you're taking the inner product. Okay, so really, this applying a DFT to this amounts to taking this linear combination of each column of the DFT matrix, and more specifically, the okay. All right, hold on. Make sure I get my notation straight. Yeah, it's a conjugate. Yeah, so a conjugate of this, which would amount to carrying out the DFT. So what you're doing is when you take the that linear combination indicated by L of applied to each of these columns, that basically carries out the basically it's a matrix product of the matrix from a problem with this. What you'll end up with is a scalar multiple of this column. The scalar multiple is the eigenvalue. Yeah. But it has to be the conjugate of this. So, yeah. Okay. But yeah, feel free to use the Wikipedia thing. All of you. So, okay. Other homework questions? Or are you just done for the day?
I have some, but that's not me.
Okay, yeah. Okay.
Feel free to share them right now. It might be useful for the rest of us.
Well, it's 14C and 15D.
Oh, okay. So 14C is one I was just talking about.
But 15D, yeah, well, 15D you should only do 2.
Right.
So, 15D? 14. Oh, 15C. Whichever. The last one on 15.
Yeah.
What was the other one I had? What was it?
Oh.
Sorry, guys.
Oh wait, we happen to get through all of them, or
Well, no,
oh, she probably memorized the book.
no, you're not. I had a question right here. So, bam.
You can print it.
Yeah, well. I don't have a printer at home, so. 14C, 14D, 15C, 2B, I got 2B, 2D. I'm gonna get 2B. So just 14C, 14D, and 15C. What was 14C again? I think I already asked you though, I just need to work on them. So. 14C, observe. I already know to do that. D is what we just talked about. Yeah, okay. Well, any questions?
Okay. Does anybody else have any questions? Okay.
All right.
Well, alrighty then.